Yeah, good morning, everyone. I am Naresh Kumar, working as assistant professor in the Department of Electronics and Communications at B.V. Raju Institute of Technology. Here in this lecture series, I am going to explain about subject called analog and digital communications. So coming to the course outcomes and prerequisites, for studying this particular subject, you require the basics of signals and systems, where you are going to study what is a signal, what is a system, and you require the probability analysis of a particular signal, whereby you can get the probability of error expressions, so that you can analyze the system performance by using this probability of error expressions. So coming to the course outcomes, so students will be able to generate and demodulate the amplitude and frequency modulated signal, and the student can be able to identify the power content and spectral characteristics of the system, and afterwards you are going to get the insights of pulse analog modulation schemes. Thereby it will be extended to the digital modulation scheme, where you are going to study various modulation schemes such as ASK, PSK, FSK, which are used in the modern communication systems. And then you will be analyzing the probability of error for the various digital modulation schemes, so that the performance of the system can be analyzed by using the probability of error as well as bit error, right? Bit error rate. So these are the textbooks which you are going to study, which you are going to use these textbooks for as a reference. So like Sam Shanmugam is the textbook which is very widely used for analyzing the digital communication systems, whereas Sam Shanmugam communication systems will be used for analyzing the analog part, right? So coming to the course overview, so various topics were discussed. Since it is analog and digital communications, you will have first part as analog communications and second part as digital communications. If you look at the various modules or various analog and digital communication systems, so you have a different classification here based on the type of carrier which you use. So based on the type of carrier which we use for modulation, we have three types of modulation schemes. This is explained in a form of this mind map. So where if the carrier is of continuous carrier, then we call it as CW modulation scheme. Where the carrier is continuous in time, then we call this as analog modulation schemes, right? If the carrier is a pulse signal, we call this as, these two comes under pulse modulation schemes, where the pulse will be the carrier for pulse modulations, as well as digital modulation also will require a pulse as a carrier signal. Now analog modulation is divided into two parts. One is amplitude modulation and another one is angle modulation, right? Amplitude modulation and angle modulation. In amplitude modulation, we have various types based on the characteristics of the output signal. We have conventional AM. We will also call this as DSB-SC, that is double sideband suppressed carrier, and we have DSB-SC, that is without carrier. So DSB, this is FC, DSB-FC, and we have DSB-SC, where it is called as double sideband suppressed carrier to reduce the power content of the signal. And we have another modulation scheme known as SSB-SC, single sideband suppressed carrier. Then we have VSB modulation scheme, which is used for TV transmission. And coming to analog modulation, angle modulation schemes, we have two types: frequency modulation as well as phase modulation. We will come to know what are the various equations governing these two modulation schemes, as well as this one. This amplitude modulation is totally covered in Unit 1. Unit 1 will be covered by this particular topic, and Unit 2 will be covering this Unit 2 will be covering this angle modulation scheme, where we will have a frequency modulation as well as phase modulation. In frequency modulation, again we have wideband frequency modulation and narrow band frequency modulation, and these two comes under this analog modulations will comes under continuous wave modulation. And next third unit will be covered in this particular pulse modulation schemes, where you are going to define the pulse modulation schemes. There we have various modulation schemes like PAM, PPM and PWM. So this is the third unit first part we will be covering this pulse analog modulation schemes. Thereby you will be studying how to convert an analog sample value into a digital sample value. So that will be covered by the third unit second part. Third unit second part, we will be covering this pulse digital modulation schemes, where we can call these modulation schemes as analog to digital converters, where we will be studying how the analog signal can be discretized and that discrete sample will be converted into a digital sample by making use of various techniques called pulse code modulation schemes, differential pulse code modulation scheme, and delta modulation schemes, as well as adaptive delta modulation schemes. So once you get the digital information in this particular part, you'll go to how to transmit this particular digital information over the carrier, continuous carrier. For that, we have various modulation schemes. These are called as lower order modulation schemes, digital modulation schemes. Lower order means you are going to make use of the binary digits for the transmission of these signals, where amplitude shift keying and phase shift keying, frequency shift keying are the basic binary modulation schemes which we study. And then coming to the higher order modulation schemes, we are going to have to increase the speeds of the modulation communication system. We'll go for MRA schemes, where instead of using binary waveform for representing the digital data, you're going to make use of ternary data or quaternary data or octal data, so that you will be getting various modulation schemes. These are called as higher order modulation schemes, where you are going to study QPSK, quadrature phase shift keying, and 8 PSK, then 16 PSK and QAM modulation schemes. So after this, you're going to study the error performance of these particular digital modulation schemes under the AWGN channel by making use of matched filter concept. So that will be covered in unit 5. So these particular digital modulation schemes, how to generate all these digital modulation schemes, what are the characteristics of those digital modulation schemes, will be covered by in this particular topic in unit 4. Okay, now in this particular lecture, we will be concentrating on how communication is done and what do you mean by communication. Communication refers to conveying of the information or transmitting the information from one place to another place. Okay, so the information which you want to convey may be in the form of analog or it may be in the form of digital. If the information which you want to transmit is analog in nature, then we call this as analog communication. Otherwise, if the information is in the form of digital or else in the form of binary data, then that such modulation schemes will call it as digital communications. So if you look at the various communication systems which come across, so the communication systems, initial communication systems were started with the telegraphy. This is the device which you use for telegraph signal generation. Then afterwards drastically increases this technology to telephony, where the voice signal can be transmitted over the cable. And then the broadcast type of transmission, you might be knowing this is the radio communication, where you can broadcast the signals through the radio, and you can receive the signals by using this particular device. And you have satellite communications and radio navigation and aircraft communications, and so we have so many communication systems we will have. And if you look at all these communication systems, different communication systems will work at different frequency. The frequency is a very important term, where the signals are going to be transmitted over the system. The communication systems can be a wireless communication system or else wide communication system. If you look at these two, the first one as well as second one, these two are said to be a wide communication system, whereas the third one is the broadcast type of communication system, where single transmitter will be there, multiple number of receivers will be there. Whoever want to get the signals, they can tune to that particular frequency and get the signals. Okay, and this is a satellite communication. This is also a broadcast communication system of wireless type, right? So these are the various communication systems which come across. Different communication systems will work at different frequencies. Okay, if you look at any communication systems, we have major building blocks are given like this. This is the major block diagram of a communication system. So first of all, we need to generate the information. The information source may be a voice signal or digital data, whatever may be. For instance, if the message signal is a light signal or picture signal, so if you come across analog communication system, so the information source will be generated by our vocal cord, that will be generated generating the information in the form of sound, and that sound signal has to be converted into a form which can be transmitted. So for that, the sound signal will be converted into an electrical signal by making use of a transducer. Transducer is nothing but it will convert one form of energy into another form of signal, and the signal which is generated from the vocal cord is a sound signal. That signal has to be converted into electrical signal, for which we will be using a microphone. So by using microphone, we can convert the acoustic signal into an electrical signal. Okay, so this transmitter is used for this is also a type of transducer which will be used to convert this electrical signal, where this particular electrical signal can be transformed into a form where this can be radiated. So radiated means we need to convert this electrical signal in such a way that it can be traveled over a longer distance. For that, we are going to make use of transmitter. Transmitter will accept the electrical signal and it will convert it into an electromagnetic signal by making use of a term called as antenna. Of course, antenna is again a device which will convert an electrical signal into a electromagnetic signal. We can call this as another type of transducer. So once it is transmitted, channel is nothing but we have so many types of channels: band pass channel, baseband channel. Band pass channel is nothing but generally it is a wireless channel where you don't have connection between the transmitter and receiver. The signal will be transmitted over the free space, and if you look at the baseband channel, then the transmitter and receiver will be connected together with a physical cable, where you need not radiate the signal, just we need to give the sufficient energy to travel over the cables, right? So the channel, in this channel is a medium through which the signal is going to be traveled, right? So while the signal is traveling over the channel, noise will be added to that particular signal which is traveling over the channel, and it will disturb the signal characteristics. So the receiver will receive the signal which is transmitted by the transmitter. Okay, and the receiver work is to remove the noise components, as well as it will demodulate the signal. So that it can be read by the human being. Right? For that, again, you are going to make use of a receiving antenna, where the electromagnetic signal will be intercepted by the receiving antenna. That electromagnetic signal will be converted into an electrical signal, equivalent electrical signal. That electrical signal will be given to again a transducer. So in this particular case, we are using a transducer as a loudspeaker which will accept an electrical signal which is directly proportional to the received electromagnetic signal, and will be given to the destination, or else human ear can be able to get that particular signal. So this is the overall normal working of a communication system, where the electrical signal or else the sound signals can be modulated and transmitted over a longer distance. Now here I have used a term called modulation. What is modulation, first of all? Is it not possible to transmit the signal without modulation? If modulation is not used, then what are the problems which are associated with that? What is the need for modulation? First of all, modulation is nothing but, modulation is defined as a process by which some of the characteristic parameter of the carrier wave is varied in accordance with the instantaneous value of the message signal. Here, what do you mean by message and what do you mean by carrier here? Message is nothing but the information which you want to transmit. Carrier is nothing but which will act as a catalyst, which is a high frequency signal. so that a low frequency signal can be converted into high frequency, so that that signal can be traveled, or else that signal can be converted into electromagnetic signal, so that it can be traveled over a longer distance, for which we require a high frequency carrier. So how it will be? So what is the need for modulation? We'll discuss. So if you look at the human voice signal, the human voice signal's frequencies will be from 300 hertz to 3400 hertz. 3400 hertz. This is the frequency of the human voice signal. If you want to transmit this signal as it is, if you consider the channel as a free space, then you require an antenna. So the antenna parameter or the antenna height can be in the orders of lambda. So let us take the antenna height is lambda by 2, which is used to radiate the signal. So then let us take the half wave dipole. So lambda is the wavelength of the signal which you want to transmit. So you know that C is equal to F lambda. So from this we can calculate the lambda value as C by F. So C is nothing but 3 into 10 power 8 meters per second divided by the frequency. Let us take higher frequency. I am taking, let us take, for instance, for simplicity of calculations, I am taking 3 kilohertz is my signal to be transmitted over the system, right? So now in this particular case, if you write this one as 10 power 3, then the lambda value will become 10 power 5 meters. Okay, so now if you calculate the height of the antenna, it is 0.5 into 10 power 5 meters, or else you can say it as 0.5 into 10 square kilometers. 10 square kilometers. Is it possible to erect an antenna of 10 square kilometers? So no. So it will be giving you 550 kilometers. 50 kilometers. Erecting an antenna of 50 kilometers is not a feasible idea, right? So that is why, to reduce the height of the antenna, what is the only option we have? I have to increase the lambda value. I have to decrease the lambda value, so that the height will be decreased and your height of the antenna will be decreased. So for decreasing the lambda, I have to increase this particular frequency. So here, how to increase this frequency? By making use of a carrier signal. So the carrier is a high frequency signal which will be used as a catalyst for translating the low frequency signal, your message signal, to the high frequency carrier, so that the translated signal will be in the FC range, so that the antenna height can be reduced. Antenna height can be reduced. This height can be reduced. So the first point is to reduce the height of the antenna. And next point is, so the low frequency signals cannot be radiated by antenna, and to radiate the signal effectively through the antenna, you require modulation, so that modulation will convert a low frequency signal into high frequency signal, so that that signal will be at a speed of light, so that can be radiated over the free space. And if you consider the multiple number of signal sources were there, so all the signals are at the same frequency, 300 to 3.4 kilohertz. So if multiple signals were generated, then it is very difficult for you to transmit the signal within the space, right? So some noise which is coming from the outside may be interfering the original signal, so that your signal may be lost. At the receiver end, you cannot identify which signal is which signal you are receiving. So to avoid that, you are going to segregate the voice signals or message signals in frequency non-overlapping bands, so that the signal can be transmitted without any overlapping nature, so that you can easily make use of the filters at the receiver, so that you can easily get the signals back. So to avoid the noise and interference causing from the other signals, you require the modulation by which you can have a non-overlapping slots allocated for each and every individual signal source. Okay, and another point is to overcome the equipment limitations. So if you look at the amplifiers and filters, they will work at a particular frequency band only satisfactorily. So it is very difficult for you to design a filter at a frequency which is emitted by the signal source. So already in the market, the available equipment will be there. They will be working satisfactorily at a particular frequency. So if you want to make use of those equipment directly to transmit your signal, so you require to convert your signal to that particular range where the equipment is working, where the equipment like amplifiers or filters are working at a particular frequency. So your signal can be translated to that particular signal, that particular frequency, and can be those equipment can be used and you can transmit easily. Okay, so in that way, this equipment to overcome the equipment limitations, you can use these particular modulation schemes where your low frequency signal will be translated to high frequency signal. And another important one is very important. It is multiplexing. So multiplexing is nothing but if we have a single channel, if you want to transmit multiple number of signals, then you will be going for multiplexing, where multiple source signals can be multiplexed and can be transmitted over a single channel, and at the receiver end, from the multiplexed signal, you are going to get back the individual signals. This multiplexing can be done in two ways. One is the frequency division multiplexing, another one is time division multiplexing. In frequency division multiplexing, by making use of a unique carrier for each and every signal, you can have a non-overlapping frequency slots like this. So this is one slot, this is channel 1, this is channel 1, this is channel 2, this is channel 3, this is channel 4. Okay, like this, 4 signals can be transmitted over a single channel by having a guard band in between the two channels, and first signal will be modulated to a frequency FC1. Second signal will be modulated to a frequency FC2. Third signal will be modulated to FC3. Fourth signal will be modulated to a frequency FC4, so that there will be a non-overlapping structure for the incoming signal spectra. This is FTM. And TDM is nothing but you are going to have the samples of the signals, and each signal will be sampled at regular intervals. Okay, within the sampling duration, you are going to send the signal 1 sample, signal 2 sample, signal 3 sample, signal 4 samples, like that, and that will be repeated. That we will discuss in detail about the time division multiplexing whenever you are discussing the sampling process, right? So as of now, the FTM will be used to segregate the signals in frequency, whereas TDM will be used to segregate the signals in time. So generally FDM is said to be an analog multiplexing techniques. This is an analog multiplexing techniques, This is said to be a digital multiplexing technique, Okay, so this is why the modulation is required. So now what are the types of modulations? So just now I told you that the modulation is a process by which some of the characteristic parameter of the carrier wave is varied in accordance with the message signal, right? So now if you look at the high frequency carrier, generally a carrier wave will have its amplitude and its frequency and phase. So the carrier can be written as C of t. So C of t is equal to, let us say, the amplitude of the carrier is AC, and I am taking a cosine signal AC cos 2 pi FCT plus pi. So where FC is the frequency of the carrier, FC is the frequency of the carrier, and this is the amplitude of the carrier, and this is the phase of the carrier, signal. Now some of the characteristic parameters of the carrier will be varied, right? What are the characteristics which are defined for the carrier? Amplitude, frequency and phase. Now these two comes under total angle of the signal. So I can classify the modulations as, one is by changing the amplitude, you can get amplitude modulation. In short, we'll write this as AM, amplitude modulation. Then by changing the total phase angle, we'll call it as angle modulation. Angle modulation. Angle modulation, right? So now in this angle modulation, again you have two parameters called, one is frequency. So we'll call this as frequency modulation. Then you have a phase of the signal carrier, that is, you can call this as phase modulation scheme. Phase modulation scheme. So we have total 3 modulation schemes where the amplitude of the signal can be changed, that is carrier signal can be changed, and the angle of the modulation, angle of the carrier signal can be changed. If you look at the angle modulation schemes, we have 2 parameters, one is frequency, another one is phase modulation. Now you can look at the waveforms. See here, this is the signal which you want to transmit. This is a signal with frequency, let us say for instance it is, the frequency of the signal is FM. Okay, so then you are going to make use of a high frequency carrier. Let us say the carrier frequency is FC, high frequency carrier, okay, FC. Then if I apply the amplitude modulation, where, what is amplitude modulation? Amplitude modulation is a process wherein the carrier amplitude will be varied in accordance with the amplitude of the message. So this is the amplitude. How amplitude is varying? Amplitude is varying sinusoidally. Hence your AM wave amplitude will also vary sinusoidally like this. You can look at the envelope. This is also varying sinusoidally. So this is amplitude modulation, AM. Now, if you look at the frequency modulation, this is the carrier signal, which is a high frequency carrier. Let us take, this is the varying modulator. As the modulating signal voltage changes, the frequency is also changing. You can look at this here. Similarly, the phase modulation, almost the phase modulated signal and angle and frequency modulated signals are looking similar, except a time delay or phase delay. So these are the definitions which govern the amplitude modulation as well as frequency modulation. Amplitude modulation is nothing but the amplitude of the carrier wave is varied in accordance with the instantaneous value of the message signal, whereas the frequency modulation is the process by which the frequency of the carrier wave is varied in accordance with the amplitude of the message signal. Similarly, phase modulation. The phase modulation, the phase of the carrier wave is varied in accordance with the instantaneous value of the message signal or amplitude of the message signal. So, in all these three cases, the parameter of the carrier wave is varied in accordance with the instantaneous value of the message signal. So, you are not changing the characteristics of the message, you are changing the characteristics of the carrier signal. Okay, so to transmit your message signal which is at low frequency, I am making use of a carrier of high frequency so that the low frequency modulating signal can be translated to high frequency and can be radiated. Right. Now we will see how to describe these equations, how to get the content of the signal, how to get the time domain as well as frequency domain equations of the signal, so that you can have more insights about the things, right? If you look at the time domain equations of AM, let us assume that your message signal is, M of t, for instance. Let us take the message signal is M of t. This is your message signal. And let us say the carrier signal is C of t, which is equal to carrier signal. Now, just now I told you that the carrier is C of t is equal to AC cos 2 pi FCT, for instance, plus pi actually. For instance, I am making this pi is equal to 0. Initial phase equal to 0. If that is the case, the modulated signal can be written as S of t. These are the notations which I'll use. S of t is equal to your carrier signal C of t plus some sensitivity factor Ka or some constant, we will discuss that, Ka into C of t into M of t is the AM wave. Okay, so here if you look at the output of the signal S of t, which is a high frequency signal which amplitude is given by, so I can take C of t common. So I can write 1 plus Ka M of t into C of t. Means the carrier amplitude is 1 plus Ka M of t, means your modulated signal amplitude, modulated carrier we call it as, is directly proportional to the message amplitude. That is why we call this as amplitude modulation. Amplitude modulation. Now if I substitute C of t here, then I can write this as AC into 1 plus Ka M of t into cos 2 pi Fc t. This is the standard AM equation where M of t is the message signal and AC cos 2 pi Fc t is the carrier signal with frequency Fc. Always this Ka is called as amplitude sensitivity factor. So the units for this are per volt. Means the device which you use to get the AM signal, it will have some sensitivity. How much sensitive the modulator is for the variations in the amplitude. That is, in AM, the amplitudes are mapped onto the carrier amplitudes. So, how the carrier amplitude is varied according to the change in the input signal. If the input is changed by 1 volt, message signal is changed by 1 volt, that 1 volt is how it is reflected as the amplitude of the carrier signal. How much 1 volt is converted in the form of carrier amplitudes. So, how much sensitive the modulator is 1 volt is converted into 1 volt change in the carrier amplitude. So, that parameter will be given by the amplitude sensitivity factor. Now, always to get the envelope of the signal, this is the envelope, AC into 1 plus Km of t is the envelope. Envelope means an outer shape of the signal. So, if you look at this one, so this is, let us say, this is your message signal. This is the message signal. So, your carrier signal is somewhat like this. This is the carrier signal. Okay, high frequency carrier. Then the modulated signal will be looking like this. This is the envelope actually. Inside it, you will have a carrier signal. You will have a carrier signal like this. So, now this will be looking like your message signal will be looking like the envelope. Envelope means outer shape of the signal. This is the outer shape of the signal. To this we call it as AM signal, where to get this particular envelope which is looking like your message, always this particular parameter 1 plus Km of t must be less than or equal to 0. Less than or equal to 0. So that always this Km of t mod must be less than 1. Always Km of t must be less than 1 to have the outer shape as your message signal. So, this condition must be satisfied to have the envelope which is looking like the message signal. So, this Km of t must be less than 1. This is one condition. Another condition is always the carrier frequency must be very greater than the bandwidth of the message. Where W is the highest frequency of the message signal, or else the bandwidth of the signal. If these two conditions are met, then the modulated signal will follow the amplitude of the message signal. Otherwise, the modulation cannot be defined or determined by making use of envelope detector. That we'll discuss later, right? So now, based on these two conditions, what happens if Km of t is greater than 1? So always it must be Km of t mod must be less than or equal to 1. Here, another definition called modulation index. Another definition is called modulation index, where the absolute maximum value of Km of t, this is the Km of t value into 100, we call this as mu. Generally, it is modulation index. So this modulation index will give you the characteristics of the modulated signal, how depth the modulated signal is, how depth the modulation signal is. Okay, how depth the modulation signal is. Always this mu should be less than or equal to 1 to get the signal demodulated by using envelope detector. Now we will see the various cases where you will have mu equal to 1, mu greater than 1, and all those things, right? Now if you look at the signal, AM signal, let us consider this is the message signal which you want to transmit, okay, and the carrier signal I am drawing here, just to draw the constant carrier amplitude, I am drawing the straight lines here. This is the carrier signal. Now your modulated signal will be like this. This is the modulated signal, that is I am drawing the envelope here. So inside it you will have the carrier of the same frequency here. This is your, always here Km of t mod must be less than 1. This is mu less than 1 case, right? We call this as under modulation. Now if you look at another case where this Km of t is equal to 1, then I can draw like this. Still the shape of the signal is same. So this is mu equal to 1. We call this as exact modulation. This is exact modulation. If you look at the over modulation case, where your signal will cross this axis, like this. Inside it you will have the carrier. So whenever it is crossing 0, a phase reversal will be there, then you will be getting the signal. So now if you look at the envelope is not following your message. So always we try to avoid this particular situation. This situation we call it as over modulated. So this over modulated signals, this mu value is greater than 1. Or else Km of t mod is greater than 1. This we call it as over modulated signal. These over modulated signals cannot be detected by envelope detectors. That we will discuss in detail in the next sections, right? Now if you look at the frequency domain description of AM signal, so previously we have seen the time domain equation. What is time domain equation? S of t is equal to AC into 1 plus Ka M of t into cos 2 pi FCT. So this is the time domain equation of the AM signal. Time domain equation of AM signal. Now in time domain we cannot get the frequency content of the signal. So I would like to get the bandwidth of the signal. Whenever you modulate the signal, how much bandwidth we require for transmitting the signal. For that, definitely I need to know the frequency content of the signal, for which we require frequency domain analysis. To get the frequency domain analysis, I require a Fourier transform. Okay, so the Fourier transform will convert a time domain signal into frequency domain signal, so that the frequency content of the signal can be analyzed, so that you can get the bandwidth of the signal. Now let us assume that, for instance, m of t, we don't know what is the signal it is. Let us assume that m of t is constituting a Fourier transform pair with m of f. M of f is the spectrum of the m of t, where the bandwidth of the signal is w, that is highest frequency component of the signal is w. Okay, so if that is the case, now if you consider the signal s of t is equal to let us say AC cos 2 pi fct, just I am expanding it, plus Ka into AC m of t into cos 2 pi fct. Right. So now, if I apply the Fourier transform for this, the Fourier transform for AC cos 2 pi fct is given by 1 by 2 or else AC by 2 into del of f minus fc plus del of f plus fc. From the signals and systems basics, you will get the Fourier transform for the AC cos 2 pi fct is given by this expression. Okay, right. So based on that, you can get the Fourier transform. See, I am writing this as S of f, capital S of f is equal to, so AC by 2 into del is nothing but delta function or Dirac delta function, impulse function. So fc f minus del of f minus fc plus del of f plus fc plus, so this Ka AC is constant. So you have a property called modulation property or shifting property. According to that, x of t multiplied with cos 2 pi fct, let us take x of t is constituting a Fourier transform pair with x of f. If I multiply with cos, or else x of t into e power j 2 pi fct will constitute a Fourier transform pair with x of f minus fc. X of f minus 1 means if x of t is multiplied in time domain with exponential, in the frequency domain, the frequency will be shifted by that much amount fc. So here Haas will consist of two parameters, e power j 2 pi fct and e power minus j 2 pi fct by 2. So this is nothing but x of t into e power j 2 pi fct plus e power minus j 2 pi fct by 2, right? So if you look at that thing, so x of t is multiplied with e power j 2 pi fct once and x of t is multiplied with e power minus j 2 pi fct once, right? So here it is consist of two parameters and another parameter is by 2 is there, I am writing over here. Now x of t place you have m of t. So m of t Fourier transform is m of f. Hence, as per this shifting property, you will get here m of f minus fc plus m of f plus fc. This is a frequency domain representation of AM signal. If the message is m of t. Now, if you look at the spectrum of the signal, this is the equation which governs the spectrum. If you draw the spectrum, let us say for instance, message signal is having bandwidth W. So this is symmetric. Let us say for instance, I am taking the signal spectra as like this. You can take any spectra, but it should be a symmetric one. So W and minus W, this is, let us say, m of f. This is my assumption. So this is the spectrum. Now, if you look at the carrier is nothing but you will have a delta functions. You will have delta function set plus or minus fc. So you have delta function with magnitude AC by 2. So you have another delta function located at minus fc with equidistance. This is 0. So this point is the spectrum of the signal at f is equal to 0. So this is frequency. Now, if you look at S of f, S of f is having delta functions. This is actually C of f. Then if you consider the S of f, will have delta function at, this is del of f minus fc, means you'll have delta function at fc with magnitude ac by 2. You have another delta function at minus fc with magnitude delta, ac by 2. Then you have a message component at fc, right? M of f minus fc, that is m of f is shifted by plus fc, means the same thing will be shifted here. Whatever the thing is there, 0 will be shifted to fc, w will be shifted to fc plus fm. So like this will be the shift. So here you will get fc plus w. Here you will get fc minus w, the same component I am writing. So similarly here, this is minus fc plus w, this is minus fc minus w. So this is the spectrum of AM signal. This is the spectrum of AM signal, right? So now if you look at this, the frequencies which are above fc, are called as upper sideband frequencies. This is USB frequencies. The frequencies below fc are called as lower sideband frequencies, LSB frequencies. So this is the frequency spectrum of the AM signal, frequency domain description. So from which, what is the bandwidth required for transmitting? This is the bandwidth of the signal, right? Message bandwidth is W. Whereas what is the transmission bandwidth here? This is the total bandwidth, right? So what is that? This is W, this is W. So total bandwidth, transmission bandwidth, I can write it as transmission bandwidth is equal to twice the message bandwidth. So AM transmission bandwidth is 2W. Okay, so we'll stop here. We'll continue in the next class.
Like, share and subscribe. Hit the bell icon for more updates.